Copy code from Claude desktop, paste into your editor, copy the result back. Over and over again. This frustration sparked a revolution. In this episode, we'll dive deep into the Model Context Protocol. How it was born from frustration, the problems it solves, and its elegant architecture. You'll learn about servers, clients, transports, and how they work together to transform chatbots into powerful agents. 2024, Anthropic. David Soria Parra, a software engineer, was frustrated. He was building developer tools, using Claude Desktop daily, and constantly copy-pasting between tools. But David had been working on something else, the Language Server Protocol. LSP provides one protocol to connect any IDE to any language server. It solved the MXN problem for code editors. David had an insight: what if we did the same thing for LLM integrations? One protocol for all AI tools. Connect any LLM to any integration. Solve the MXN problem for AI agents. MCP solves three major problems. First, integrations. Before MCP, you needed a custom connector for each model and each integration. Claude plus GitHub? Write a connector. GPT-4 plus GitHub? Write another connector. Claude plus Linear? Another one. With MCP, you have a universal connector. One server for GitHub works with all models. One client per application accesses all servers. It's like USB-C for AI integrations. Second, distribution. Before MCP, tools were bespoke and tightly coupled to applications. Hard to share between teams, impossible to distribute publicly. With MCP, you can share servers on GitHub, run them as remote services, and anyone can make their data AI ready. Third, two-way communication. MCP isn't just about sending data to LLMs, it's also about receiving from them. Client asks server to list tools, server responds with the list. Client calls a tool, server returns the result. This bidirectional flow enables autonomous agent behavior. Let's explore MCP's three-layer architecture in detail. At the top, we have the host application with its LLM. This could be Claude Desktop, Cursor, or your custom agent. The host is where the user interacts and where the LLM makes decisions. The MCP client sits between the host and the server. Think of it as a translator and coordinator. It discovers what tools and resources are available, manages the connection lifecycle, and routes messages between the LLM and the MCP server. The transport layer handles all communication. For local servers, we use STIO, standard input and output streams. For remote servers, we use streamable HTTP. The transport ensures messages flow reliably in both directions. At the bottom, the MCP server provides the actual capabilities, tools that can execute code, resources that provide data, and prompts that guide interactions. The server registers its capabilities during initialization and waits for the client to call them. Here's how a tool call flows through the architecture. The user asks a question. The LLM decides it needs a tool. The client sends a list tools request through the transport to the server. The server responds with available tools. The LLM picks one. The client sends a call tool request with arguments. The server executes the tool and sends back results. The client passes results to the LLM. The LLM formulates the final answer for the user. This entire flow happens seamlessly, often in seconds. Let's explore the host application and client in detail. A host application is any app that runs an LLM and can integrate MCP. This could be an IDE like Cursor or Windsurf, a chatbot like Claude Desktop, an agent framework, or even an AI-powered terminal like Warp. The beauty of MCP is there are no restrictions, any application can become a host. The MCP client is what makes the host application MCP ready. It sits between the host and the servers, acting as a translator and coordinator. The client has three main responsibilities. First, discovery. When the client connects to a server, it discovers what capabilities are available by calling list tools, list resources, and list prompts. This gives the LLM a menu of what it can do. Second, connection management. The client manages the full connection lifecycle: initialization, operation, and shutdown. It ensures messages flow reliably and handles errors gracefully. Third, message routing. When the LLM decides to use a tool, the client translates that decision into the proper MCP message format and sends it through the transport to the server. When results come back, the client passes them to the LLM for processing. Here's a key insight: one client can only talk to one server. If your application needs to access multiple servers, you'll need multiple client instances. This is by design. It keeps the protocol simple and each connection focused. The host application is responsible for managing multiple clients if needed, coordinating their results, and presenting everything seamlessly to the user. Now let's dive deep into MCP servers, the powerhouse of the protocol. Servers provide three main primitives that make AI agents truly powerful. First, tools. Tools are executable actions, functions the LLM can call to do real work. This could be searching the web, reading files, querying databases, sending emails, or anything you can code. When you register a tool, you define its name, description, and input schema. The LLM uses these to decide when and how to call your tool. Second, resources. Resources are data sources that provide context to the LLM. Think of documents, log files, database records, configuration files, or API responses. Resources can be static files or dynamically generated data. The key is they give the LLM access to information beyond its training data. Third, prompts. Prompts are interaction templates that guide LLM behavior. They're like reusable prompt engineering patterns. You can define prompts with variables that get filled in at runtime, creating consistent, optimized interactions. Servers can be local or remote. Local servers run on your machine using STIO transport, perfect for development, personal tools, or when you need direct file system access. Remote servers use streamable HTTP and can be deployed anywhere, ideal for team collaboration, cloud services, or when you need scalability. Any programming language can implement an MCP server. Python and TypeScript have official SDKs that make development a breeze. But the protocol is open, so you could build a server in Go, Rust, Java, or even Bash if you wanted. The key is implementing the standard endpoints: list tools, call tool, list resources, read resource, list prompts, and get prompt. Once you do that, any MCP client can connect and use your server. Here's an advanced feature: sampling. Normally, the LLM in your host application calls tools on the server. But with sampling, the server can request completions from the host's LLM. Why is this useful? Imagine a research server that needs to generate multiple research questions, or a code review server that needs to analyze different aspects of code. The server can request sampling to get AI-generated content as part of its tool execution. This creates powerful recursive agent patterns where servers become mini-agents themselves. Every MCP connection follows a three-phase lifecycle. Phase 1, initialization. The client and server exchange capabilities, negotiate protocol versions, and establish the connection. Phase 2, operation. This is where the magic happens. The client lists tools, the LLM decides which to use, the client calls them, and results flow back. This phase continues until the task is done. Phase 3, shutdown. The client terminates the connection, the transport handles cleanup, and resources are released. The built-in transports manage this lifecycle automatically, so you can focus on building your server logic. Let's see MCP in action with real-world examples. Local servers include file system servers for reading and writing files, database servers for querying your data, and Git servers for version control operations. Remote servers include web search APIs, cloud storage services, and SaaS integrations. Framework servers wrap existing AI frameworks like LangChain or AutoGPT, making them MCP compatible. The beauty is they all use the same interface, the same discovery mechanism, and the same calling convention. Let's recap what we learned. MCP provides a universal interface for AI integrations. It solves the MXN problem, making distribution easy and enabling two-way communication. The architecture has three components: servers that provide tools and data, clients that connect LLMs to servers, and transports that handle communication. The connection lifecycle has three phases: initialization, operation, and shutdown. MCP was inspired by LSP and is rapidly becoming the standard for building AI agents. In the next video, we'll build our first MCP client and connect it to real servers. If you found this helpful, hit that like button. Subscribe to follow the rest of the series where we'll build real MCP servers and clients. Drop a comment with your questions or what you'd like to see next. See you in episode 3.